Good morning. Hope everybody had a great break. Hopefully you came back refreshed. We've only got this week left of new material, and then remember next week is the final exam. That reminds me, if you haven't already signed up for your exam time, please make sure you get that done this week. I just need to have an idea of when everybody's going to be taking their final exam. Again, if you need to change that date or time, please just let me know. It's not a big deal. I just need to make sure that I'm available in case you do run into issues as you're taking your exam. I want to make sure I'm there so that I can actually fix those issues immediately and you're not stressed about the final. Okay, so just make sure you sign up for a time. Let me know if you have any questions about that. I did also open up the exam review before the break, so if you haven't seen that already, you can start taking a look at that. The plan right now is to get through the rest of, we only got 2 more sections, so hopefully between today and tomorrow we can complete those 2 sections. That'll leave us with Thursday for review. If we need an extra day, I will meet on Monday of next week also, just to get through any problems in the exam review that we don't have time for this week. But hopefully we'll get through everything this week. If not, though, I will have an optional meeting on Monday if you want to come for that review session. Okay. Don't forget, though, you do have to schedule your exam by the end of this week so that I know when you're taking it, and then you have to take it before Friday of next week. Okay, so Friday of next week is when I have to have all exams in. That way I can get them graded over that weekend because my grades are going to be due at the first of the following week. Okay. So I scheduled out dates in Collaborate through the end of the summer session, but we won't actually be meeting all of those days. So like I said, Thursday of this week is our last official class meeting. And then if we need Monday of next week to finish up the review, then we'll meet on Monday. But those would be the absolute last days that we would possibly meet. Okay, so nothing beyond Monday of next week for sure. All right. The other thing is we still do have 1 more test and 1 more homework left. So just don't forget there is a homework on the Chapter 6 material. It's not due until Tuesday of next week, right? But we'll finish up the material, by middle of this week. So if you want to go ahead and get that done so that then you only have to worry about the final exam, it's there, obviously. Go ahead and be working on it, but it's technically not due until Tuesday of next week. The other thing is the test number 5. Because it was listed as Wednesday of next week, I'm going to leave that due date. I'm going to open it up tomorrow, though. So if you want to go ahead and get it done, you can go ahead and get it done anytime you want to this week. And then again, that way all you have to worry about next week is the final. Okay, so it's technically not due until Wednesday of next week, but you'll have it available midnight tomorrow night if you want to get started on it and finish it up before the weekend. Okay. Test 5 is also not going to be in Respondus, so it's open note, open book. So if you just want to, print it out, take your time with it, answer a question here or there, that's perfectly fine. There's no time limit. It's not in Respondus. You don't have to be on camera for test 5. Okay, so use whatever resources you want to complete that one. Just remember that that material will be on the final exam, and the final exam is proctored in Respondus, so you will still need to know how to do those problems. I'm just not going to make you be on camera for that final test. Okay? All right, let's see. I think that's all I've. Oh, last thing. I just posted a teacher evaluation form for me. If you have time, I would really appreciate it if you would go through and do that. It just gives me some good feedback about what things work, what things didn't. That way I can improve the class for future semesters. Okay, so if you have a chance, it's just a survey in Google Forms. So if you have time, there's a link there in the announcement section. If you would complete that, it's anonymous. It won't affect your grade in any way. It's completely optional. Okay, but if you have time to do it, I would really appreciate it. Okay. No time limit on the 5th test, open note, open book. So again, it'll open at midnight tomorrow night. Complete it whenever you can. Just make sure you turn it in by Wednesday of next week. Okay. So final test, there is no, it's basically just going to be a link in Blackboard when it posts. You'll just download the PDF. You can print it out if you want to. You can complete it on notebook paper if you want to, whichever way is preferable for you. But then you'll still scan it and upload it like you normally would. You just don't have to go into Respondus to access it. Okay. Any other questions about anything now? All right, and if you do have any questions right throughout the week, or once the test opens, if you're unsure of what to do, things like that, just email me, let me know. I'll be happy to answer any questions you might have. Okay, but again, just keep in mind those due dates. Last homework due Tuesday of next week, test 5 due Wednesday of next week, final exam no later than Friday of next week. And please, again, if you haven't already scheduled your time for the final, go ahead and do that. And if you need to change your exam time from what you've already scheduled, just let me know, and I can move that around for you. Okay? All right. So section 6.4, right? So like I said, we've only got 2 more sections left. Hopefully we can get through this one today, and then the last one tomorrow. So we're looking now at derivatives of log functions, right? So we've looked at exponentials. That was what we did last week, right before the break. Now we're going to look at what if we have a logarithmic function, how do we find the derivative of that? And then we'll also work backwards and find antiderivatives also. All right, so derivative of natural log function. If we're taking the derivative of the natural log of u, right, where u is some inside function inside your natural log, we're going to do 1 over u, and then we're going to multiply by the derivative of the inside, right? So it's a chain rule, but it's 1 over the inside times the derivative of the inside. All right, and if you just had natural log of x in general, the derivative of just natural log of x then would just be 1 over x, because then the derivative of the inside would just be 1, so it's 1 over x times 1. All right, so let's take a look at this one, see if we can find the derivative of natural log of x cubed plus 1. So again, if you're comfortable doing it without the u substitution, by all means, that's fine. You can skip that step. I'm going to do the u value for now, though, just to make sure we're comfortable with it. What could we let u be equal to this time? Good. So everything inside the x cubed plus 1 is going to be our u value. So I'm going to rewrite this now as y equals natural log of u. So when we find the derivative, then we're just going to follow that formula we just saw. So the derivative of natural log of u is going to be 1 over u times the derivative of u. So we just need to multiply by u prime, or du dx, however you want to write that. All right, so now we need the derivative of u. So what's our derivative for u going to give us this time? Good, 3x squared. So now we have all the pieces we need. So y prime is going to be equal to 1 over the u value. So 1 over x cubed plus 1 times the derivative of u, which is 3x squared. And so at that point, we could just multiply those together, put the 3x squared in the numerator. So our final answer is just going to be 3x squared over x cubed plus 1. So again, all we're doing here, if it's a natural log function, you're finding the derivative, it's 1 over the inside times the derivative of the inside. Any questions on that one? And then again, obviously, if you can find ways to simplify, especially when you get these fractions like this, always do that. In this case, that fraction doesn't simplify, so that answer is good. All right, so let's take a look at this one. So we're going to find the derivative of natural log sine x. All right, so what do you want to do first here? Okay, and so what's our u value going to be here? Good, so let u be equal to sine of x. I'm going to rewrite this then as the derivative of natural log of u. All right, what can we do next? So what's the derivative of natural log of u going to give us? Let's start there. Okay, so the u prime piece, right, is going to be cosine. And then good, the derivative for natural log of u is 1 over u. And then don't forget, because it is a u substitution, it's a chain rule, we do have to do the u prime here. All right, so now we have all of our pieces. Now we can substitute in. So we're going to get 1 over the u value, which is sine of x, times our u prime value, which is cosine x. Again, just like the last one, now we can put these together. That's going to give us cosine in the numerator over sine in the denominator. And then what's another way we could write that? Cotangent, right? So cosine over sine, same thing as cotangent. So we could simplify this all the way down to cotangent x now. Now, if you had left that as cosine over sine on a test, I'm going to give you full credit, right? Because you've shown me you understand the u substitution. You know how to find the derivative of natural log, right? So if you get it to here, I'm good. But cosine over sine is cotangent. Any questions on that one now? All right. So now we've got f of x equals the square root of the natural log of x, and we want to find the derivative. All right, so how would you start this problem? So if we do antiderivatives of trig functions and get functions involving natural log, is that fine? When we get to the antiderivatives, it will be possible to get natural logs as our result, yes. We'll get to that point though, right? So for right now, let's just focus on the derivatives. And then when we get to those antiderivatives between the end of this section and section 6.6, then we'll start looking at those antiderivatives. All right, so what would you do first on this one if we're looking for the derivative for square root of the natural log of x? Okay, good. So we're going to let u be equal to the inside, but the inside this time is the natural log of x. So then we can rewrite this as f of x equals the square root of u. All right, now what can we do? All right, and so if we find f prime here, how are we going to do that? So if you got square root of u there and you're looking for the derivative, okay, it is going to be a power rule, right? So let's rewrite that square root with an exponent. So we can rewrite this as u to the 1/2. Right, and now we can apply our power rule. So f prime of x, we're going to get 1/2 u to the negative 1/2. And then again, because it's still a chain rule, we have to multiply by u prime. Okay, so just don't forget, if you ever have square roots, rewrite them as fractional exponents, and then you can actually use our power rule to find that derivative. All right, so now what else do we need to find? Good, we need our u prime, so we can substitute everything in there. What is u prime going to be equal to this time? Okay, so 1 over, but not u, because in this case we're taking the natural log of x, so it's just going to be 1 over what? 1 over x, right? So remember, if it's just natural log of x, your derivative there is just going to be 1 over x, because the derivative of the inside is just 1. All right, so now we have all of our pieces, so we're going to have f prime of x is equal to 1/2. The u value here is natural log of x to the negative 1/2. And then we're going to multiply that by u prime, which is 1 over x. All right, now don't leave the negative exponent, right? So what can we do with that? Good. Move it to the denominator, make it a positive exponent. In this case, we already have a 2 in the denominator and we have an x in the denominator. So all that's going to be left up top is a 1. And we're going to have our 2x and then natural log of x to the positive 1/2. Or if you want to write that as a square root of the natural log of x, that would be fine also. But this right here would be our final answer now. Nothing else we can do to simplify that. Any questions on that one? All right. Let's take a look at this one now. So derivative of natural log of x plus 1 over the square root of x minus 2. All right, so what's our first step going to be this time? Okay, so what are you going to let u be equal to? Okay, good. Everything inside the natural log, so that entire fraction, x plus 1 over the square root of x minus 2. Which means we're looking for the derivative of natural log of u. Now we know that's just going to give us 1 over u times u prime, which means we need u prime. How are we going to find u prime this time? Good. It is going to be a quotient rule, so we need to figure out our f, our g, and then use quotient rule to find the derivative. Remember, f is always the numerator, so that's going to be x plus 1. G is always the denominator, so that's going to be square root of x minus 2. Okay, so now we need f prime and g prime. So what's f prime going to be? Just 1. Good. And then how are we going to find g prime? Okay, good. So it's technically a chain rule, right? And it's going to be a power rule with a chain rule. So again, because it's a square root, I'm going to write it as x minus 2 to the 1/2 power. And so our g prime then, we're going to have 1/2 times x minus 2 to the negative 1/2 times the derivative of the inside. What's the derivative of the inside? Just 1, right? So in this case, we don't even need that part. So this is really just going to be 1/2 x minus 2 to the negative 1/2. And I'm going to leave it as that for now until we do all of our substitution, and then we'll figure out what to do with the negative exponent once we put everything in there. All right, so now remember our quotient rule to find u prime says we're going to start with the g function, so that's going to be x minus 2 to the 1/2 times the derivative of f, which is just 1, minus, then we have our f function, which is x plus 1, times the derivative of g, which is 1/2 x minus 2 to the negative 1/2, all over g squared, so x minus 2 to the 1/2 squared. All right, now let's clean that up a little bit before we go over here and substitute it into our 1 over u times u prime. So we've got u prime equals, well, x minus 2 to the 1/2 times 1 is just x minus 2 to the 1/2. Got that piece, minus. And then over here, I'm just going to move this 1/2 to the front of this product. So 1/2 x plus 1 times x minus 2 to the negative 1/2 over. And then x minus 2 to the 1/2 squared is just going to give us what? So not, well, so the exponent would become 1, right? And so the overall value here is going to be what? X minus 2. Good. We have x minus 2 in our denominator. All right, now I want to get rid of, actually, let's not. Let's leave it like this for now, and then we'll simplify once we actually put the fractions together. Okay, so I'm going to keep what I've got here. I'm going to move it over here now. So we have 1 over u. So that's 1 over x plus 1 over the square root of x minus 2. Well, if I do that, what's that really going to give us? So if I do 1 over a fraction. Yeah, it's just the reciprocal of the fraction that we've got in the denominator, right? So I can rewrite this then as the square root of x minus 2 over x plus 1 times, and then we have this fraction here, x minus 2 to the 1/2 minus 1/2 x plus 1 times x minus 2 to the negative 1/2 all over x minus 2. Any questions up to that point? Okay, now I just need to simplify what we've got here. So combine these fractions, multiplication. So I need to distribute the square root of x minus 2 to each of these terms now, right? So where the subtraction is to each of those two. When I multiply the square root of x minus 2 times x minus 2 to the 1/2, what's that going to give us? Just x minus 2, right? Because this is like x minus 2 to the 1/2 times x minus 2 to the 1/2. When we add those exponents, it gives us a 1 again. So we have the x minus 2 now left over. And then I need to do the same thing down here. I'm distributing this. And notice I have this x minus 2 to the negative 1/2. So when I do that, what's going to happen? Okay, so not 0. The exponent becomes a 0, so the overall value then becomes what? 1, right? Because anything to the 0 power is going to become 1. So we have this x minus 2 to the positive 1/2, x minus 2 to the negative 1/2. Those exponents cancel out. So that becomes a 1. So now all that's really left is the 1/2 and the x plus 1. Because then it's multiplied by a 1 over, and then we have our x plus 1 times x minus 2. All right, now all that's left to do is just to distribute the 1/2 here, combining like terms we have in the numerator, and we should be good. So now we have x minus 2 minus 1/2 x minus 1/2 over x plus 1 times x minus 2. And now if we combine like terms up top, that's going to give us a 1/2 x, and then negative 2 minus 1/2 is going to give us a negative 2.5 or a negative 5/2. So we get minus 5/2, and then x plus 1, x minus 2. Now, I'm perfectly fine with that answer right there. The other thing you could do, if you wanted to get rid of the fractions, you could multiply top and bottom by 2 here. So this would be the same thing as just 1x minus 5 over, and then we have a 2 down here now, x plus 1, x minus 2. Okay, so that's probably the most simplified version. Okay, but again, if you were to stop right here, even with those fractions in the numerator, I'd be okay with that. Any questions about that one now? Now, just so you know, be expecting problems similar to this one on test 5 or even possibly the final exam, because again, this combines a lot of different stuff, and so I can test a lot of information in a single problem by giving you something like this. Right? We've got a chain rule here, we've got a quotient rule here, we've got the derivative of the natural log function here, and then just some basic algebra to simplify it at the end. But this actually tests a lot of different knowledge. Okay, so problems like this are what you can probably expect to see. All right, example 5. I'm going to find the absolute min value for this function x squared times the natural log of x. All right, so if we're looking for an absolute minimum, what are we going to do first? Okay, good. So we need to take the derivative, find our critical numbers, because anytime you're asked for a min or a max, that's exactly what we're going to do, no matter what type of function it happens to be. Okay, so we need our derivative, f prime of x. So what are we going to use to find the derivative this time? What rule do we have here? So our function's x squared natural log of x. It is a product, right? So we're going to have to use product rule here. So again, identify f and g first. So f this time is going to be x squared. Our g function is natural log of x. What's f prime going to give us? Good, 2x. And the derivative for g is going to be what? Good, just 1 over x. All right, so now remember, for product rule, it's going to start with f, so f g prime plus g f prime. So when I come back over here now, we're going to have x squared times 1 over x plus, then we have natural log of x times 2x. Right, now we can go ahead and simplify this a little bit. So x squared times 1 over x. One of those x's is going to cancel here. So we're going to get x plus, and then over here I'm just going to bring the 2x to the front. So 2x natural log of x. Okay, so there's our derivative. So what do we need to do with that derivative now? Good. Set it equal to 0, right? So anytime you're looking for critical numbers to find your min or max, always set your derivative equal to 0. Now, how are we going to solve that? Good. We have a common factor of x here, so we can factor that out. So we'll have x times, it's going to give us 1 plus 2 natural log of x. All right, now we can do what? So now that we have our factors, what can we do? Good. Set each of those factors equal to 0. So we're going to have the x equals 0, and then 1 plus 2 natural log of x equals 0. Well, x equals 0 is solved. We don't have to do anything with that. So now 1 plus 2 natural log of x. If I try to get the x by itself here, I'm going to move the 1. So we get 2 natural log x equals negative 1. Divide by the 2. That gives us natural log x equals negative 1/2. And then what would you do to solve that? Okay, good. So we're going to use an e here because remember the base of the natural log is an understood e. And so we can actually rewrite this in exponential form now. So this is going to be e to the negative 1/2 is going to be equal to x. So x equals e to the negative 1/2. Any questions about how I got that value? All right. Now what are we going to have to do? Because remember, these are the critical numbers now, right? So we have critical number at x equals 0, our other critical number at e to the negative 1/2. Good. So we need to set up a number line. Now, one thing I'm going to tell you here, because natural log of x is part of the original function, what do we know about the domain for natural log of x? Think about what the natural log function looks like graphically. Think about what its domain would be. It's only positive values. Good, right? We can't put any negative values inside of a logarithm. Okay, so this is always going to be positive. So our domain here is really only from 0 to infinity. So the overall function x squared natural log of x is going to have that same domain. So when I set up my number line now, I'm actually going to start my number line at 0 and then continue to positive infinity. Because I don't want to choose anything in the negatives because it's not going to work for the original function anyway. All right, so now the only critical number I really need to put on here then is the e to the negative 1/2, which is a positive value, right? That's just going to be 1 over e to the 1/2. So now we just need to be careful with choosing our value to the left and to the right. So 1 over e to the 1/2 power is approximately 0.6 something. Okay, so if you want to choose something between 0 and that value, what could we use? .5 works, right? So that's less than the 0.6 something. And then again, on the other side, anything bigger than 0.6, so just a 1 would work there. All right, now where are we substituting these values? In f prime, good. So I'm going to say f prime of 0.5. And again, any of those f primes where you want to substitute in, it doesn't matter. I'm going to do it right here. So we're going to have 0.5 times 1 plus 2 times the natural log of 0.5. I mean, honestly, I would probably just put all that in my calculator just to see, is it negative, is it positive? So in this case, if we do that, what does this give us? And again, all we really care about is whether it's positive or negative. It's a negative, right? So we get negative like 0.19 something. Okay, but again, all we really care about is whether it's negative or positive. Okay, now let's do something on the other side of e to the negative 1/2. So again, I went with 1, so f prime of 1 is going to give us 1 times 1 plus 2 natural log of 1. This one I can actually do by hand. Natural log of 1 is going to be equal to what? Not 1, 0, right? Because e to the 0 power is equal to 1. So natural log of 1 is 0. 2 times 0 is 0. So we really just get 1 times 1 right here. So this is going to be 1. Okay, so overall, then, that's going to be a positive value. And so what does that tell us then about e to the negative 1/2? Okay, good. It's a minimum, right? In this case, it's the absolute minimum because it's the only critical number. It never switches direction again. So we have both a local and an absolute minimum at x equals e to the negative 1/2. Now, technically, this one does ask for the minimum value. So what do we have to do now? Good. Plug that back into the original equation to find the actual value. So we're going to say f of e to the negative 1/2. It's going to give us e to the negative 1/2 squared times the natural log of e to the negative 1/2. Well, what's e to the negative 1/2 squared? Okay, good, right? So negative 1/2 times 2, because we would multiply the exponents, is going to give us e to the negative 1. And then what's the natural log of e to the negative 1/2? Just negative 1/2, right? Because natural log of e to some power is just going to be equal to the exponent. So this is just a negative 1/2. Now I can move my e to the negative 1 into the denominator. We already have a 2 down there, so this is going to be negative 1 over 2e. That is our minimum value now. Any questions on any of the steps for finding that minimum value now? All right. We're going to skip example 6. Okay, so example 7. We want to find f prime of x. And this time we've got f of x equals the natural log of absolute value of x. All right, now I want you to think back whenever we dealt with absolute values and we were finding derivatives. What did we do? What did we always do with our absolute value functions when we were trying to find derivatives? Good. We rewrote it as a piecewise. We're going to do the same thing here. So I'm going to split this thing up. I'm going to say f of x equals. All right, so we're going to say, well, it's going to be equal to the natural log of positive x whenever x is what? Greater than, and now in this case, remember, we can't be equal to 0 inside of a natural log. So we're just going to ignore 0 altogether and just say greater than 0. Remember, there's going to be an asymptote for the natural log function at 0, so we never want to be equal to 0 there. What about the other piece of this then? What's the second piece going to look like? Okay, but remember there's an absolute value inside. So his question was, isn't it going to be undefined if there's a negative inside the natural log? Absolutely. But remember, the absolute value is going to make it positive anyway, right? And so that's why we have to, split it up and say, well, if it's positive, it's just going to be the same as natural log of x. But now if it's negative, what's it going to look like? What are we going to have to do to it? That's right. Okay, so we're going to do natural log of negative x whenever x is less than 0, because now if we have negative values, when you put the extra negative in front, it makes it a positive, and so now we're really taking the natural log of a positive value, right? Okay, so we're allowed to put negative values in there because the absolute value is going to make it positive anyway. Just can't have 0. All right, so now that we've got our piecewise function, now I want to think about the derivative, and we're going to think about the derivative of each piece. So if we have natural log of x, what's the derivative for the top piece of our piecewise going to give us? Just 1 over x, right? We know that derivative. So this is going to be 1 over x wherever x is greater than 0. Now, what about the derivative of natural log of negative x? Okay, so be careful here, right? If you think about this one, u is equal to negative x. The derivative of that is going to be negative 1, but we're doing 1 over negative x times negative 1, which is actually going to give us what? 1 over x, right? Because the negatives cancel out now. And so this is actually 1 over x also, wherever x is less than 0. Okay, so because you end up with that double negative, 1 over negative x times the negative 1, those negatives cancel, and you actually get positive 1 over x. So really, the derivative here for the natural log of the absolute value of x is always 1 over x, so long as x is not equal to 0, right? That's the one value that we can't have here. So we still have to do it as a piecewise function, right? Or you at least have to say where x is not equal to 0. Any questions about that? Okay, now, this is why this is important. When we start working backwards now and find our antiderivatives, we have to remember that if you have a 1 over x inside your antiderivative, inside your integral, it's actually going to come out as natural log of absolute value of x. Because technically, that x could be positive or negative, right? We're not sure, and so we have to have that absolute value bar around the x now. So the derivative of natural log of absolute value of x is technically just 1 over x, again, as long as x is not equal to 0, which makes sense because we can't have a 0 in the denominator of that fraction anyway. Okay, but now when we find our antiderivative for 1 over x, it's not just natural log of x, it's natural log of the absolute value of x. Okay, so just don't forget the absolute value bars whenever you're doing those antiderivatives now. Any questions there? All right, so we want to find to 3 decimal places the area of the region under the hyperbola xy equals 1 on the interval from 1 to 2. So what would you want to do first here? All right, so we know it's going to be an integral on the interval from 1 to 2, right? Because that's what we're doing. Anytime you're looking for an area of a region, it's always going to be an integral. They give us our endpoints from 1 to 2, so that's our lower and upper bounds. What else do we need now then? We need a function, right? So how are we going to write the function that goes inside here then? Good. Solve that equation for y, and then whatever we get is what's going to go in there, which means I need to divide both sides by x here. So we're going to have y equals 1 over x. So our function is actually 1 over x. And then just don't forget your dx, right? Because that's our independent variable now. So that's how we're going to find the area of our region. So again, anytime it's the area of a region, it's always the integral. They should give you the endpoints. Those are going to be your bounds for your integral. And then you need your function in terms of an x value for now, right? When you get to Calc 2, if you go on to take that, then you'll actually do integrals in terms of x's or y's or sometimes both. Okay, so for now, though, everything's going to be pretty much in terms of x. All right, now, when we do this, what's the next step going to be? Okay, good. So what's the antiderivative for 1 over x dx? Good, right? So it's going to be natural log, absolute value of x. And then in this case, we don't need the plus c because we actually have limits of integration. So we're just going to go from 1 to 2. All right, now it's just a matter of substituting. Remember, always start with your upper limit. So we're going to have natural log absolute value of 2 minus natural log absolute value of 1. And in this case, it said we're going to 3 decimal places, so we can actually just put this in the calculator if you want to. Natural log of absolute value 2, same thing as natural log of 2. Remember, natural log of 1 is just going to be 0, so this is really just natural log of 2. And if we approximate that to 3 decimal places, what should that give us? Good, 0.693. So there is our answer. Any questions on that one now? All right, let's go ahead and take our break right here. So I've got 11:56, so we'll say, or sorry, 10:56, so 11:01, we'll get started back up. Yeah, Rachel, that's right. So the answer to number 7 was just the piecewise 1 over x, where x is less than 1 or x is greater than 0. All right. So what I'm going to do now, I'm actually going to show you with this example that we just finished how we can actually check our answers in the calculator. So if you have a graphing calculator available and want to grab it real quick, I'm going to show you some steps on the calculator for how we can actually check answers to integrals that have limits to them. Okay, so we can't find just general antiderivatives, but if we're looking for a specific area under a region, we can actually do that in the calculator now. So let me switch over to my calculator. There we go. All right, so first step, we're going to go to y equals, and we're actually going to put in whatever our function is. So in this case, we have 1 over x. And so again, you have to solve for y first, right? So we can get y equals some function, right? And then we're going to put that function into y equals. All right, now what I'm going to do next, I'm going to go ahead and look at my graph. Okay, so there's the graph of 1 over x. And we need to make sure that our window actually has the values that we want for our x values. In this case, we're going from 1 to 2. That is in the general window that goes from -10 to 10 and -10 to 10. Okay. If your values fall outside of your window, then you're going to need to go to window and actually adjust those values. But again, because 1 and 2 are in our window, then we're fine. Okay. Now, the next thing we're going to do is we're going to go to our calculate menu. So we press the second key, and then the trace key is where calculate is. So second trace. And then notice if you look down at number 7, there's our integral. Okay, so we're actually going to calculate the integral of f of x dx now. So we're going to select number 7. And now it's asking us for the lower limit. What was the lower limit of integration for the last one we just did? On example 8, 1, right? So we put in our lower limit of 1, we press enter. Now it's asking for the upper limit. What was our upper limit? That was 2. So now we press 2, we press enter, and it's going to actually do the calculation for us and tell us that our integral now is equal to 0.693, right? So that's the area under that curve. Now, if I change my window a little bit, you can actually see, I'm actually going to change this, just go from like -3, oops, to +3. And we'll do the same thing here, -3, +3. All right, and I'm going to regraph this because I just want to show you, it's hard to see on that wider screen there, but if I do my calculation again, zoomed in a little bit, from 1 to 2, notice it actually shades in the area that we're looking at, right? So it gives us from 1 to 2 what that shaded region would look like, and then it tells us what that area would be, in this case 0.693. So anytime you want to check your answers for a definite integral, as long as you can put the function into your calculator, and then you can actually do second trace, which is your calculate, go down to your integral, put in your lower and upper limits. It'll actually shade the region and tell you what the area of that region is. Now, remember, for the most part on the test, I'm going to want exact values. So you're still going to have to show your steps, right? And so like on this one, I would be looking for natural log of 2 as the answer. Well, the calculator is not going to give you natural log of 2. It's going to give you the decimal equivalent of that. Okay, so as long as it's just asking for 3 decimal places, your calculator is good. But if you need the exact value, you're still going to have to work it out to see what that exact value would be. Okay, but again, calculator is a great way to check your answers once we get natural log of 2 to see if it matches what the calculator says the area should be. Any questions about any of those steps now? All right. Example 9. Okay, so now we want to evaluate this integral, x over x squared plus 1 dx. All right, so what do you think we might want to do first here if we're trying to evaluate this integral? Yeah, we're going to have to do a u substitution, right? So we don't want to actually move the denominator to the top. Let me just tell you why that wouldn't work, because that's a good thought, right? If we do that, we're going to end up with x times x squared plus 1 to the negative 1. We're still going to have a product there. We can't simplify it, right? And so it's still not going to really help us in determining what that antiderivative would be, right? So that's a great thought if you could then simplify it. But because we can't and we still have a product, it's still not really going to do us any good there. All right, so we are going to want to do a u substitution here. And so we just have to choose what we let u be equal to. In this case, let's go with the denominator. Sometimes it will be the numerator. So I'll tell you that, right? And so if you choose one and it doesn't seem to work out, then just choose the other. But in this case, we'll go with the denominator, u equals x squared plus 1. All right, so let's think about what we've got now if we start to rewrite this. So I know for sure I've got my u in the denominator. What do we still need to replace now? The x and the dx, right? So I still need to figure out a substitution for x dx. Well, now we can go to the u value. We can find our derivative. So du dx is going to be equal to 2x. Now we can move the dx to the other side. So du equals 2x dx. But we don't want 2x dx. We just want x dx. So what do we have to do? Divide by the 2. We're going to get 1/2 du is equal to x dx. So now in place of x dx, I can put a 1/2 in a du. So we'll have 1/2 du. Or if you prefer, right, we can put the 1/2 out front here and just put a 1 in the numerator there. Any questions about doing the u substitution for this one? All right, now we can find our antiderivative. So what's the antiderivative for 1/2 1 over u going to look like? Perfect, right? So keep your 1/2 as the coefficient. Antiderivative for 1 over u is going to be natural log absolute value of u. And because it's an indefinite integral this time, we're going to have the plus c. And once we have our antiderivative, last step, we got to put the x values back in there. So we're going to have 1/2 natural log absolute value of x squared plus 1 plus c. So this answer right here is good. Now, in this case, x squared, right, is always going to be greater than or equal to 0. When you add 1, it's automatically going to be greater than 0. So everything inside there is going to be positive regardless. So if you wanted to drop the absolute value bars on this one, you could, and just say natural log x squared plus 1 plus c. Okay, I would take either answer, okay, but in this case, technically, absolute value bars aren't necessary because it's going to be a positive value regardless in there. Any questions on that one now? All right, let's take a look at this one. So we have a definite integral this time from 1 to e, natural log x over x dx. All right, so what do you think we should do first this time? Okay, good. We're going to have to do a u substitution. So again, we just have to decide what we're going to let u be equal to. In this case, we are going to want to use natural log of x as our u value. And this is what I was saying before. Sometimes it'll be the numerator, sometimes it'll be the denominator. It just kind of depends on what you've got there. Okay. And again, if you would use the denominator, let's say u equals x, well, that derivative is just 1. That's not going to get us what we need left over, right? So we're going to go with u equals natural log of x. So again, I'm going to start rewriting this thing, which means this time we're going to have u in the numerator. And so we're still trying to replace what then? Yeah, the x and the dx, but notice here, the x this time is in the denominator. And so we just have to make sure that when we replace it, we're getting an x in the denominator, not in the numerator. Okay? Well, du dx this time is going to be equal to what? 1 over x, right? So there's our x in the denominator, just like we want it. And so now we can do what? Good. Just move the dx to the other side. So we get du equals 1 over x dx. That's exactly what we're trying to replace. So this is just going to be a du now, and this is just over 1. Any questions about that u substitution? All right. What else do we need to do here? Okay, good. We need to change our limits of integration, so we're going to plug those into our u value to find those new limits. Okay, so I'm going to start with my lower limit. That's a 1, so we're going to get natural log of 1, which is equal to what? That's just 0. Good. And then if we do our upper limit, we're going to have natural log of e, which is that one's equal to 1. Good. So our new limits of integration are from 0 to 1. All right, now we just need our antiderivative. Well, u over 1 is just u, right? So we're just looking for the antiderivative of u, which would give us what? So not natural log, right? Because remember, it would have to be 1 over u to give us a natural log. So how are we going to find the antiderivative of u this time? There we go, right? So we raise the exponent by 1, we divide by the new exponent, so that's just going to give us 1/2 u squared, evaluated from 0 to 1. Okay, so even though the original function had that natural log in it, right? Once we get it in terms of u, it's just a basic power rule, right? So just raise the exponent by 1, divide by the new exponent. Now we can plug everything in. So we're going to have 1/2 times 1 squared minus 1/2 times 0 squared. And what is that going to simplify to? Just 1/2, right? So 1/2 times 1 is 1/2. Second part here just gives us 0. And so overall, that's just equal to 1/2. Any questions about that one? Now remember, this is one you could actually put in the calculator now and check, right? You would just put natural log of x over x as your function. Then you'd go to your graph. You'd put your lower limit at 1, your upper limit at e, and it should give you 0.5 as your final answer. All right, so now we want to calculate the integral of tangent x dx. All right, so first off, do we have a general antiderivative for tangent? Is that one of our trig functions that we just know the antiderivative for? Is it? So if you look back through all your antiderivatives, sine, cosine, all that stuff, it's not, right? So this is not one that was in that table when we did antiderivatives for our trig functions. Secant squared was in there, secant x, tangent x was in there, but just the antiderivative for tangent x is not, right? Because it's not a basic trig antiderivative. So what we're going to actually want to do here is use our trig identities to rewrite this somehow so that we can actually do it using some of the strategies we've learned and actually evaluate what this would be. So how could we rewrite tangent x? What's the most common way to rewrite tangent? Sine over cosine, right? So let's try rewriting this as sine over cosine and then see if we can actually find the antiderivative based off what we know now. So what do you think we might want to do with that fraction at that point? Good. What do you want to let u be equal to this time? All right, so we'll go with cosine. All right, and this again is one of those where it's not obvious which one to go with, so you could try the numerator, see if it works. If you did the numerator this time, the derivative of sine is cosine. The problem is the cosine needs to be in the denominator, and you're not going to get that, right? So that's why we have to use the denominator as our u value this time. Okay, so now I'm going to start to rewrite this in terms of u. So u is going to go down here. That means we're still trying to replace the sine x and the dx now. Well, if I find my derivative, what's du dx going to be equal to this time? Good, negative sine of x. Right, now we want sine x dx. So I'm going to go ahead and move my dx to the other side. So we have du equals negative sine x dx. Again, we don't want a negative sine of x dx, so we need to move the negative over now. So that's going to give us negative du is equal to sine x dx. So now we end up with a negative, so we have negative 1 du. All right, now we can find our antiderivative. What's the antiderivative for negative 1 over u du going to look like? Okay, good. Almost, except in this case, because it's a negative, we just need to make sure we put a negative in front, right? So it's going to be negative natural log absolute value of u plus c. Another way to think about it, if you want to put the negative 1 out front here and then just make that a 1 over u, right? Just make sure you bring down the coefficient of negative 1 there. So we get negative natural log absolute value of u plus c. Now we just have to plug the u value back in, which is cosine x. So we get negative natural log absolute value of cosine x plus c. There is our antiderivative. Any questions about any of the steps for that one now? Okay, and this is why the antiderivative of tangent is not one of our general trig antiderivatives, is because we get a natural log as part of the antiderivative now. Okay, so we don't do that when we do basic trig ones. In general, that's a good strategy, right? So yeah, if you have one that you don't just know the antiderivative of up front, then I would say think about your identities, think about how you could rewrite it. It's not always just going to be sine and cosine, right? We do know the antiderivatives for those for sure, but you also know the antiderivative for secant x tangent x. You know the antiderivative for secant squared x, right? So it could be that you're getting it in terms of those instead. But yeah, try to get it in terms of one of your trig antiderivatives that you already know. That's the key. Okay. Any other questions there? All right. Now, this next slide gives us the formula for the antiderivative for tangent x dx. It's natural log of the absolute value of secant x plus c. That's not what we just got. Okay, so what I want to talk about now is how did they get that as their answer and we got something different. So this is the formula they're giving us now, is the antiderivative of tangent x dx is natural log absolute value secant x plus c. So I'm going to go back. Let's look at our answer. And let's compare it with what they got. So are these answers equivalent? Is there anything we could do with the answer that we got to make it look like the answer that they've got there? Okay, all right, good. We know the reciprocal of cosine is secant, right? So if there was a way to flip the cosine, then we'd have exactly what we need. Well, what would cause that to flip? Okay, the negative, right? Where would the negative need to be to make the cosine flip? So think this is the same thing as like natural log absolute value 1 over cosine x plus c, right? Because that's the reciprocal of cosine. So where would you need a negative to make it look like that? To go from cosine x to 1 over cosine x. It needs to be in the exponent. Well, how do I get that negative into the exponent now? And I guess it's not really a question of how, but why. Okay, it needs to go inside the natural log. And if you remember back to your properties of logarithms, if you have a coefficient, you're allowed to move it into the exponent of your logarithm. So this is the same thing as natural log absolute value cosine x to the negative 1 plus c. So whenever you have a coefficient in front of a logarithm, any kind of logarithm, you're allowed to move it to the exponent. That was a property of logarithms. Once we do that, now we know that this is equal to 1 over cosine, and then we know that 1 over cosine is secant, and so these two answers are equivalent to each other. Okay, so obviously on a test or something, right, I'm going to accept this answer, right, because you've shown me all the steps, right, and that's a perfectly acceptable answer. Okay, but you could also move the negative to the exponent, rewrite 1 over cosine as secant, and so natural log of absolute value secant x plus c is equivalent to the answer that we got here. Any questions about that now? And we'll review those properties of logarithms a little bit more because we've got another example coming up where we're really going to need to use those. Okay. All right. Now, the other thing on this slide is if we have the derivative of some other type of log, right? So everything we've done so far has just been natural logs. But now if we have just a general base b log of x, the way we're going to find that derivative is 1 over x times the natural log of b. And notice the natural log of where the base is b value. Okay. And if you think about it, right, the base of the natural log is e. So whenever you're finding the derivative of the base e log of x, then it's just 1 over x times the natural log of e, but the natural log of e is 1, and so this just becomes 1 over x. So that's why the derivative of natural log is just 1 over x. We don't need that natural log of b piece. But if that base is something other than e, now we need the natural log of b in the denominator. All right, so let's try this one now. So we've got log 2 plus sine x, and we want to calculate the derivative. All right, so first things first, what is the base of this logarithm? 10, right? So anytime there's no base written, we have a common log, it's an understood 10. All right, so now I'm going to do a u substitution here just to make sure it's clear where all the pieces come from. So we're looking for the derivative of the base 10 log of u, where u is 2 plus sine x. Okay, so it is going to be a chain rule this time. We're going to use that formula we just saw on the last slide to find out the first part of this. All right, so our u prime is going to give us what here? Good, just cosine x. And now if we follow the formula that we just saw, I'll go back and show it to you again, it's going to be 1 over x, which is the inside piece, times the natural log of the base, and in this case we're going to have to multiply by a u prime because it's a chain rule. So we're going to have 1 over u times the natural log of the base, and because it's a chain rule we have to multiply by u prime. Now we can start substituting everything in here. So we're going to have 1 over 2 plus sine x, natural log of the base, which is 10, times our derivative over here, which is just cosine x. And our last step here, we can just put the cosine in the numerator of this fraction just to create one fraction. So we have cosine x over 2 plus sine x, natural log of 10. And that's it. Okay. So nothing else you can really do to simplify that fraction. So we're just going to leave it just like that. Any questions about how we got that answer now? All right. Now, if we take the derivative of an exponential function where we have some base, because remember, we've already done e to the x, and that just gives us e to the x. But now if we have some base other than e, some b, then it's going to be b to the x times the natural log of b. Again, if this had been e to the x, when we take the derivative of that, if we follow this same formula, it's going to give us e to the x times the natural log of the base. But we know natural log of e is just 1, and that's why the derivative of e to the x is just e to the x. Now if we have some base other than e, we just have to remember that natural log of b piece because it's not going to become a 1 anymore. All right, so let's take a look at this one. So we've got the derivative of 10 to the x squared power. All right, so again, I'm going to do this as a u substitution just to make sure it's clear where all the pieces are coming from. So I'm going to have d dx 10 to the u, where u is x squared. Okay, so now if we follow our formula from the previous slide, it's going to be whatever the base is to the x power, in this case the u power, times the natural log of the base. So we're going to have 10 to the u times the natural log of 10, and then we have to multiply that by u prime. And what's our u prime value going to be this time? 2x. Good. So now we have all of our pieces. So we're going to have 10 to the x squared times the natural log of 10 times 2x. And honestly, whatever order you want to write this product in is perfectly fine. You can't multiply the 10 and the 2, so be careful there, right? Because 10 is being raised to the x squared. These are all just separate pieces of a product. So honestly, I'd probably leave it just like that. If you want to move the 2x to the front, you could, but nothing else we can do to simplify that. So there's your answer. Any questions about how we got that one? All right, and just so you know, on the test and on the final, I'm going to stay away from these bases other than E and your natural logs, right? So there will be homework problems where you need to know these formulas, but in terms of the test and the final exam, just focus on e to the x and natural log of x in terms of derivatives and antiderivatives, right? That's what you're actually going to see on those. All right, now the integral of b to the x dx then is going to give us b to the x over the natural log of b plus c. And notice here that b can't be equal to 1, okay? Because 1 to the x power would actually just be 1, a constant function. And so that's why b cannot be equal to 1 here. So any base other than 1. All right, so let's try this one now. So we've got 2 to the x dx. We're finding the antiderivative of that evaluated from 0 to 5. All right, so let's start with the antiderivative. What's the antiderivative for 2 to the x going to look like according to this formula then? So I just want the antiderivative for 2 to the x. What would that look like? Good, right? So we're just going to take 2 to the x, that goes in the numerator. Then we take the natural log of the base, which is 2, so natural log of 2, and then we have to remember our plus c. This is going to be 2 to the x over natural log of 2. And in this case, we don't need the plus c because we do have limits of integration. So we're going from 0 to 5 here. All right, now that we have our antiderivative, now it's just substitution. So we start with the 5. So we're going to have 2 to the 5th over natural log 2 minus 2 to the 0 over natural log 2. Now it's not asking us to round here, so I'm going to keep everything as an exact value. What's 2 to the 5th power? Good, so we get 32 over natural log of 2. What about 2 to the 0? That's going to be 1 over natural log of 2. Since I have a common denominator, I can combine these. So what's our numerator going to be? 31. Good. So we just get 31 over natural log of 2. That's an exact value. That is our answer. Now, again, you could check your answer, right? Just find the decimal equivalent of that and then use your calculator to graph 2 to the x, put in the integral from 0 to 5, and see what it gives you as the shaded region there. Just make sure it matches the decimal that you get for 31 over natural log of 2. Any questions on that one now? All right. The last example I'm going to do here is 15, but I think it's going to take me a little longer than the 8 minutes I have left. So let's stop there. We'll save that example, and I might do 16 too tomorrow. But I think I can get through those two as well as section 6.6 tomorrow. So we'll stop there. Again, the homework is posted if you want to start working on the 6.2, 6.4, and 6.6 homework. You've actually got most of what you need other than the 6.6 stuff, so feel free to work on that. Don't forget also that test 5 is due by Wednesday of next week. It is posted, so you can actually be working on that. I think that's all I've got. Oh, don't forget also, I did post the teacher evaluation, so if you have time to do that sometime this week, I would really appreciate it. Again, it's just a survey, just clicking on, strongly agree, disagree, whatever, for each of the little pieces there. So it shouldn't take too long. So if you've got time to do that, I would really appreciate it. Okay. If you have any questions about the final or about the test or the review or anything like that, please let me know. Otherwise, have a great afternoon, and I will see you tomorrow. Yeah, Anna, give me just 1 minute and we can talk. Hey, Anna, do you want to jump over to the student hours link in Blackboard, and I'll meet you there? That way, since there's still a couple people in here, I don't want to talk if you're talking about anything sensitive.
Okay, yes, that would work.
Okay. All right, I'll meet you over there.
Okay,
Yep.
thank you.